Good morning, everyone, and welcome to another live Quanser webinar. My name is Michel Levy, and together with my colleague Gemma Wang, we will be your hosts and moderators this morning. Today, we're very excited to have John Pineros. John's been part of the Quanser's R&D academic applications team, which develops content for teaching undergraduate control concepts, as well as research examples for our studio offerings. For the past 5 years, John's been involved with training end users on how to set up and use Quanser's autonomous vehicle research studio, as well as developing ROS examples for the initial release of Quanser's self-driving car research studio. In today's webinar, John will go over the improvements on the QCar ROS 1 support, as well as some upcoming releases to expand on QCar's existing ROS offering for users looking to work with ROS 2.
Hello, everyone. Thank you for the introduction, Mitch. So, um, my name is John Pineros. As Mitch mentioned, I'm an R&D engineer here as part of the academic applications team. And in the webinar today, we'll be talking about interfacing ROS and Quanser products. So, in case you don't know, Quanser is the amalgamation of question and answer. So the question today is going to be that ROS interface to a lot of our Quanser products, and the answer is going to be presented to everyone in the perspective of the QCar. And so hopefully this gives you ideas in case you already have Quanser products and are interested in interfacing them within ROS related research, or if you want to get more information about how the QCar's ROS development was developed, this will give you a little bit more insight into how that was done. And so the agenda for today is going to be motivation as to why we're going through the ROS interface for a lot of our products and what that means in terms of your research. The majority of the webinar will focus on examples that have been released on the QCar, and as Mitch mentioned, some updates on some of our content. And then at the very end, the floor will be open for questions. So, motivation. How can ROS and Quanser work together? To be able to answer this, let's look at what it means to have ROS support at a high level. So ROS, our robot operating system, can be looked at as this communication from different aspects of a robot. So this can be anything from a algorithm running on your system, getting access to hardware, or if you are using ROS packages, what those packages mean in terms of either moving a robotic manipulator, or this can be a navigation package. And so what you can think of this is this transfer of information from one node to the other in this open source aspect. Now, when you are looking at ROS itself, it can be developed in one of two ways. It can be done either using Python, which is what's most common out there in terms of starting examples, or if your research does depend on something that's a little bit more performant, you can also use C++. Now, when ROS was initially developed, as part of the computer science community, they developed a sequence of distributions that are now known as ROS1. So whenever you start out, and if you look at the content that's released on the QCar, which is using ROS Melodic, that is part of this umbrella of the ROS1 library of distributions. With more adoption of these algorithms and put into the industry, the ROS community wanted to make changes to the way that the communication architecture was developed. And so there have been new releases which fundamentally changed the way that the communication architecture was done in order to ensure more security, as that's part of what's needed in the industry. And so when this architecture change was developed, these new distributions are now dubbed as ROS2. And so it depends on where you are in your research field. If you're using algorithms that have been developed for a while, it's very likely that they were developed in ROS1. And so we can look at the current support out there, at least for the QCAR, for example, for you to continue that kind of research. If you're a new research group and you would like to get familiar with ROS, it is beneficiary to look at ROS2 because this is what's going to have the most support going forward. And there are ways that you can interface ROS1 algorithms within ROS2, as that's also a very common question. Now, when we look at the ROS platform itself, how could that be developed using Quanser products? So we have this workflow over here, which pretty much explains the ROS interface, which could be either the algorithm that you're developing, interfacing to any sort of already released package, and then the focus of what is the webinar today, which is how does the Quanser product interface with this entire system. So at first, it's looking at any sort of subscriber information for input commands from the car. This can be a manual driving example or a waypoint that it needs to go in space. And so from a first pass, you already know what part of your ROS algorithm is needed to be able to generate some sort of commands. The next step is looking at how you actually want to interface with the car. Is this going to be done via Python with the examples that we've released? Or do you require some sort of performance, which can let you go down the C++ side, which does change a little bit about how the architecture works in the background, but you still have some support. At the end, you then have to take a step back and check what kind of information you would like to publish within your network for the overall algorithm that you're using to be able to work perfectly. And so you have this combination of inputs to your user, Python examples, and then release. Because this is a network communication at the very end, you do have to consider bandwidth in terms of what kind of information you're sending and the frequency at which that information gets sent. So understanding this, ROS and the ROS community have also taken a step back and figured out what are common sensor types that are available for robots. This can be some information to a message type described for IMUs, something like 2D LiDAR, which is a laser scan message, or something a little bit more generic, like a vector message, which contains X, Y, and Z components. Now, these have been preset. And so, because these are common examples out there, odds are you might not be able to get what you're looking for. So, the ROS community also gives you the ability to create your own message using different data types. And so there's this flexibility of you being able to use what's already available or generating your custom messages. There's a full list. I've added a link here under the ROS wiki under all the common messages. This can be sensor messages, navigation messages, so you don't have to construct anything from scratch if it's already available for you. So looking at messages, what does this look like? We're looking at it from the QCar's perspective. On the left-hand side, if you've had a chance to look at our ROS examples, you know that we have a node for sending joystick commands to the car. And so when we actually probe into that message, when our example is running, we can see that it was developed using the geometry packages or the geometry messages package using the vector3 stamped message type. We can then look at what is publishing this information, which happens to be our command node, and what is subscribed to or listening to these commands, which happens to be the Q car. And so this is how we can get the car to drive around using a steering and a throttle command. We can also take a look at how that message is interpreted within a ROS network. Now, a stamped message also contains information about time, which is that header that you see at the bottom left image, which lets you know in your sequence of messages, what is the number associated to this message, a timestamp in seconds and nanoseconds, and a frame ID. Usually, frame IDs are necessary in order for the ROS network to understand within your robot architecture what is this message attached to. And then the last step is the actual vector that defines the message itself. We're using X as the actual steering command and then Y as the throttle command. Zen does not get populated, but this is us taking advantage of a message that is already available for us in order to be able to send information. Now, if you look on the sensor messages side, as I mentioned a second ago, another preset message type is the IMU. And so there's nothing subscribed to this, but the car, as it's driving around, is publishing this type of information to the network. And so here's where you have to take a step back and figure out what information you would like to publish and how you construct that message. We are using the IMU as the actual data type that we would want to send, and the configuration looks very similar to what we looked with the geometry messages. There is a header with a sequence and a timestamp, also used when you want to reconstruct the information afterwards using something like a ROS bag, which acts like a black box for a robot. You can play this information afterwards, and as long as you have a timestamp and a sequence number, you're making sure that everything is aligned when you're replaying your information back. Beyond this, the IMU message data type also has the orientation in case we had some sort of attitude estimation. But in this case, because we're just looking at the raw sensor values, you can see that what gets populated is the angular velocity, which happens to be coming from our gyroscope, and then the linear accelerations, which happen to come from the accelerometer on the Q car. And so hopefully this gives you an idea of first looking at what sensors you have available, what it looks like to read a message in your not in your ROS network, and probing it out afterwards to see if the publisher and subscriber are actually talking to each other. Now, if we take a step back and look at the Q card itself, we have a wealth of information that's available to us. Everything from the Intel RealSense RGBD camera, which gives us depth and RGB information, to the RP Lidar A2, which we've used multiple times for mapping examples, um, going everything to the lower level, which is the IMU, which I showed a second ago. We have access to wide angle cameras. And so if you happen to have another product, you can kind of take this diagram to figure out which information you actually need to publish and what information you actually want to construct your algorithm around. Taking this step back, we now look at what is the current work that's been done on ROS on the Q card as a launching point to what's going to happen next. And so if you had a chance to look at the Quanser products, you realize that for the QCar, we have a sequence of nodes that run using our hardware test, which give you access to the I/O. As I mentioned, this is a lot of the accelerometer, motor commands, steering commands, all our cameras, and our LiDAR, as well as one other additional command node, which we looked at a second ago for manually driving the car. Beyond this, we also give you examples on how you can interface with the ROS ecosystem to visualize using a visualization tool called RVIS, or a more interesting example, which is Hector mapping, which only uses the LiDAR to generate an occupancy grid. Now, if in case you're not familiar with the way that a ROS package is structured, you usually need a folder structure that looks very similar to this, where you have a high-level ROS workspace. On the car, it's called ROS1. Inside of this, there is a source directory which holds all the packages that are necessary for your application. We've released one called QCar, and inside of it, there's a sequence of XML files that define all the prerequisites from the software side. But this package also contains every node that we've developed within Python. Again, everything from the cameras to the LiDAR information to the car to also using a joystick for steering information. Now, in order for all this to work, you also need access to the Python APIs that we have available. Now, there's two specific things to consider. These right here are the Quanser APIs that give you access to low-level components of the car, like how to configure the IMU or how to configure stream information. So for the most part, these get pre-installed in the car, but if you happen to update the runtime, you can find them located at opt-quanser Python. And using a package manager like pip, you can then update the packages in case we do make releases. Again, this gets installed with the car installer runtime manager, and that gets all populated in this location. If you want to develop some Python applications on your host computer, that is another way to do this, currently available when you install them using our QUARC installer. But again, we're focusing on the QCar, and so this is the location of those files in our system. Now, because we are looking in this webinar as how we can interface our product within the ROS ecosystem. In the released examples, you'll notice the following folder structure. On the left-hand side, you'll notice a folder called QCar, which has a sequence of libraries. They don't necessarily go inside of the APIs I showed you a second ago. They act like a high-level wrapper, which lets you as the user just specify when it is that you want to read something like the gamepad or the cue card. In this case, that is block number 2, where I'm specifying that I want to talk to a gamepad. I'm specifying that publisher that I showed you earlier that has the vector3 stamped message, the number of samples I want to hold on to before the next message gets sent out, as well as how do I actually configure the gamepad itself. I want to read it. I make some decisions based on triggers and some of my joystick commands, which then turn into the actual driving commands. And then at the very end, when my node finishes, I want to close or terminate the communication to my gamepad. Then the next step is actually populating that ROS message, which is what the process command function lets us do. And so in here, this is where we saw a second ago in terminal what the overall message looks like. In this case, we're seeing how we actually populate everything from defining the fact that we're using a vector 3 message. In different examples, it could be an image or it can be a laser scan message with the ID associated to the frame itself, the time as the ROS interface lets us know, and then the vectors X and Y, which are associated with the throttle and steering commands. And at the very end, publishing this information. The way that this is set up is mainly information gets published every time that ROS sees that there's a brand new command or sensor information from our joystick. So if we happen to read our joystick at 100 times a second, then we're sending or publishing this information at 100 times a second. Now, going through all of this and finishing what has been already released for the QCar, we can take a look at the mapping example, which is a very interesting one, which takes a look at the LiDAR. We have released a launch file, which already takes RViz, launches our ROS workspace. And in this configuration here, I'm using VNC Viewer to do a remote connection to the car, and I will be rotating the car in a second, and then you'll be able to see the occupancy grid get populated as the car starts to move around. So if in your robotics application, you would like to generate a map of the environment, this could be a starting point. Again, using the Hector mapping algorithm, take this map and develop your own waypoint navigator, or if you do want to make a map of the environment. This is done with the car. If you have a different Quanser product and you would like to also use the mapping package, again, that's kind of already available if you look at the launch file that we currently have as a starting point of how you can interface a node with a lot of our current information. So that was what we or have already released. We've taken some feedback from our customers, and so here are some of the updates of the content that is currently being created. So we've taken a step back into how we've redesigned some of our libraries. A second ago, you saw that there was a folder called QCar with a sequence of libraries. We've tried to make them more user readable. In this case, we're planning on releasing what we call Python application libraries, which should let you define what it is that you're interested in. In this case, we're interested in using a Quanser product, which happens to be the QCar. And in this case, you can then initialize the car depending on the different styles or the different ways that you want to read the user inputs and outputs. In a previous webinar, we talked about using a task-based implementation where you use the timer on our DAC in order to read information. And so that's kind of the approach that we've taken, and we look at how that has been implemented in a second. Beyond this, we're looking at ROS and we're looking at what messages we would like to implement. In this case, is the same idea as the standard messages, as well as geometry for the um, information for our velocity, and another custom message, which is the battery state of the car. And we'll look at in a second as to how we decide first how to access the IO and then when we want to publish that information. Our last step is, as always, initializing our publishers, stating the type of message that we would like to use. So when we looked at the car and we looked at giving it support for ROS2, we understand that the timer, if you will, that's available on ROS could be a little bit inconsistent. And so we want to leverage the fact that we've got hardware timers on our DAC, in this case on the Q car, and we can sample information at a very fast rate. ROS may not be able to keep up with 500 hertz, but we also have to consider the higher level. Your algorithm may not necessarily need to read battery information at 500 hertz, but it might need to look at that information one time a second. Same idea with the linear velocity of the car. And so what we've done is we've used a task-based implementation where we're reading information very accurately at 500 hertz, and then we decide at what rate we want to set the various publishers, again, depending on the algorithm that we would like to use. And so how would that look like from the Python side of things? We've got a main loop, which we've already defined a second ago, is going to run at 500 hertz. We have developed a read-write function that takes in the steering commands. That would be from our joystick or anywhere in a network, as well as the LEDs that are available on the Q car. And we then split out the information that we're trying to read. In this case, this could be the IMU. And as you can see here, we're combining accelerometer and gyroscope information. We're reading the battery voltage, and we're doing a conversion for the linear velocity of the car. Now, we also have to create these actual publishers and combine that information, which is what we can see on the screen as individual sections, either for the IMU itself, or for the battery, or for the velocity. The advantage of taking an approach like this is you have modularity in terms of not relying so much on ROS for the timing. You rely on our systems for accurate data acquisition while you're using ROS to do the lower level signal um, communications and data streaming. This also gives you the ability, in case part of your algorithms are using something like cameras, which are very bandwidth intensive, you can actually go in and verify if you actually need information from the IMU faster than you need it from your image processing algorithm, in case that was what was dependent. Looking at images and the way that they've developed, we've taken a step back and looked at what would be the most efficient way of streaming image information. In this case, ROS has a compressed image message as one of the data types that's available, which gives us the ability to send information much faster than the regular image message type. Now, this all is limited depending on the actual distribution and ROS that's available. So in the version of ROS 2 that's on the car, which happens to be dashing, compressed messages are not cannot be visualized using RVIS2 or the robot visualization tool. And so what we've also developed to give you the ability to view these compressed messages is a separate node which will actually spawn a little window and you can actually view the RGB information. In this case, we're also looking at streaming depth, as that's part of what the RealSense can give you. But this data type is indeed supported by Arvis. And so you can see that there's flexibility whether you're using the robot visualization tool or a custom node that displays this information. So in a high level, what does this look like? So this is a view from my workspace, and I've got the car on the ground. I'm doing a remote desktop connection. So if there is a little bit of choppiness, that's just due to the bandwidth itself. It's actually at the proper frame rate that it needs to be on the car. I am moving my hand around so that we can visualize changes in RGB information as well as the corresponding depth data. So if I play this again, the depth data is being visualized in Arvis on the left-hand side, and I'm now moving my hand around and visualizing this using the custom node that we have developed. This is using a compressed image message so that we can guarantee that we're streaming image information as fast as possible. And so the last step is now to look at the LiDAR itself as another of the main great sensors that we have for our QCar. We have made some changes in the way that we treat the LiDAR information. Part of this was checking the actual 360 scan to make sure that it is compatible with the way that the ROS ecosystem is expecting this information. And we did some data type or some image um, conversion or data conversion to reorient the LiDAR to match the way that the ROS scan message definition is expecting this to look like. When we visualize it with Arvis, this is the same scan that I was using a second ago for the occupancy grid map, but this is now only looking at the RP LiDAR itself and what that scan more or less looks like. And we can see that it is compatible with the map that we've developed. We see the corners of the workspace that I was at, along with some other objects that are bouncing back and forth from the LiDAR itself. How were we able to do some of the data filtering and formatting? We, again, using our Python API, more or less took a step back, looked at the current scan and the number of angles that are available. We flipped this information around since ROS and the laser scan message expects information to come in counterclockwise, and then did some clever filtering to figure out what was the minimum point, what was the maximum point, and then populate the angles in between in order for us to get a valid message that can be visualized within our RVIS visualization tool. So more or less to wrap this up, we looked at prerequisites for developing any sort of custom ROS node using our hardware. So this would be getting access to our custom Quanser APIs, figuring out if you're going to be using ROS 1 or ROS 2 as your development environment, figuring out the actual message types that you're interested in using, and then moving on to that workflow of a ROS algorithm, developing a subscriber and a publisher with the IO access in the middle, and having that workflow going. Then we switch to looking at it from the perspective of the QCar and the work that's been released right now with our own APIs and the ROS 1 package that's available, and then updating upcoming support for ROS 2 since we have had requests for ROS 2 support on the QCar. Again, this is ROS 2 dashing as that's the version that's supported by Ubuntu 18.04, which is the version of Linux that's available on the car. And again, some changes to the data acquisition and the way that we publish our topics for efficient use of our bandwidth. And for that, thank you for your attention. And now the floor is open for questions.
Thanks a lot, John, for the great presentation. And as you said, I think we can proceed to answer some questions. So please use the meeting chat window and submit any questions that you that I'm sure you guys have. Okay, we have one here, John. What other Quanser systems are supported in ROS?
Thanks for the question, Mitch. So officially, the QCar is the first product that has ROS support. We do have a limited example that's available for the QARM if you are interested. That way, you can use or send the arm a desired position in the workspace, or you can command the individual joints. Those are available if you get the instructor resources for the QR.
Okay, great, thanks. So QCar and QARM. Yeah, we have one question here. Where can I get these packages? Um,
So for the released example on the QCar, you can take advantage of the packages by looking at the core modules section that's available on our Research Studio resources. The core modules has a subfolder called the QCar, which has the actual um, visualization for the QCar in Arvis, as well as the QCar node, command node, visualization of the CSI cameras and RGBD. That's available there. From the user, you would have to transfer the QCar folder onto your actual QCar within that ROS 1 and source workspace that I showed at the very beginning, and then recompile your overall package. That way, you'll then be able to take advantage of ROS run if you wanted to run the nodes individually or using the ROS launch to visualize all the data of the car. So that's currently available again as part of our Research Studio resources, which you can download from our website.
Great, thanks a lot. So another question here from Germa Tiwoli, part of my pronunciation. Do you currently have the QCar available in ROS Gazebo simulation?
There is a released version of ROS of QCar for ROS 1 that you can import into Gazebo. There are some components in there that are ideal in terms of the actual image parameters. So when you import a car, you have to create a URDF definition for the car itself that more or less is very similar to the physical car that you have. As part of that, we have to make a virtual representation of the wide angle cameras as well as the RGBD. So that information is already available within the QCar package. You can take a look at the URDF. Just keep in mind that if you compare something like the wide angle camera that the URDF gives you, it might be a little bit different than the physical camera on the car. Obviously, the physical camera on the car has a little bit of color shift, a little bit of noise, which is not present in the URDF, but for the most part, is fairly close.
Great. Okay, so we got two more questions here. One from Mutaz Rialet. Can we use MATLAB instead of Python?
MATLAB instead of Python for ROS. So As of right now, what we've tested is using Python in order to stream information to a Simulink diagram and make some sort of processing and send that information back. If you wanted to know what that might look like, you could look at the QCar's released content. And inside of it, there is a example for using stream communication to send images. Now, you don't necessarily have to send images. You could configure that to be something like the QCar's IMU and stream that information to a Simulink diagram within MATLAB and Simulink. We also have examples of stream clients. And so you can start to send that communication and it starts to look very similar to what we've done or what ROS does, which is setting up a communication architecture where you're sending information from the Python side to the Simulink side and back. In that case, you're also using the Quanser Communications API, which is fairly robust at making sure that packages are sent and received using bidirectional communication, which would be very beneficial in an application like this.
Okay, and the last question from Carlos Bajorquez. Is there an app API for the QBall X2?
An API for the QBall X2. My understanding is the QBall is not supported in Python. Mitch, you can confirm that as well.
That's correct. Yeah, the QBall
Yeah,
is not. Yeah, not currently anyway. And the QBall has been, that was our previous system, previous to the AVRS, and yeah, there's no plans on supporting that right now. But having said that, please reach out to us via email, and we can find out a little bit more about what exactly you're trying to do, and maybe we can help. Um, I think that's all the time we have today. If you guys do have more questions, then please don't hesitate to send us an email. Go to our Quanser.com page and send us any questions you have, right? So this brings us to the end of our webinar. And John, again, thanks for the great presentation. And a big thank you for everybody that attended today. Again, please visit our website at quanser.com and check out our LinkedIn page to find out more about our systems and any upcoming webinars. And I'd like to wish everybody a great day and thank you.
great time. Bye bye, everyone. Have a good day.